All right, I'm going to get started now. Can somebody just send me a quick chat message to let me know if they can hear me? All right, so folks can hear me. I set you all to mute when you joined. I will try and keep the chat window open for questions. I think you're able to unmute yourself. So if you want to shout out a question, you can do that too, but otherwise just use the chat window. So the first thing that I'm going to go through is the infamous question number 9. So let's go all the way back to the beginning. I'm going to hide some of this and then just try and make this a little bit bigger. Let's just scroll all the way back. So I'm going to do question 9 and then question 10, and then I'll probably just open it up for general questions. But clearly there's a little bit of confusion about question 9. Basically, what this comes down to is build a star schema and then do some OLAP operations using SQL on top of the star schema. And I wanted you to do that for the Sequila database. So I reloaded the Sequila database as a second version of itself. So I've now got 2 copies. Part of the problem that I had going through this in previous recitations is I was going through a star schema I had done previously in a previous version of this class. And so I was kind of showing you tables that I created and they were partial results. So I decided to go back and do it from scratch. So I reloaded the Sequila database from scratch, and I basically created the schema and loaded the data. And I'll explain what I did. I created, I think, 5 tables, and I'll go through them and explain why I created them. So just kind of as a refresher, this is what a star schema looks like. There, in the simplest version, there's a fact table. The fact table has one or more metrics. These are measurements or things that happened. So a typical metric would be, how much money, what was the total dollar value that this store earned in a day? This is kind of a single granular fact. Sometimes it even goes down to the individual transactions, and that's what we're going to do in Sequila. So when you go all the way down to the lowest level of granularity, it's an event, like something happened. One of the things, a huge concept in data-driven decision support and OLAP and star schema is the granularity of things. At the finest grain, it's basically every event or every transaction, but you can decide to sort of look at higher granularity. If you go up, getting coarser things, it's a roll up and an aggregation. If you go down, it's a drill down. But since there's not a huge amount of data, I just decided that I was going to keep every individual event as a fact, and you'll see that in a second. So there's a few metrics, and then there's a set of foreign keys into dimension tables. And so that's what a star schema looks like. There's a little bit more here, like quantity sold, amount sold, average sales. This might be a metric for a day. And so then there's like the item, what was the thing, when did it happen, and then where did it happen in the organization? So in which part of my internal organization did this happen, and where? So these are by far the most four most common dimensions. Right. So this is a fact. Sort of when you like learn journalism in high school, it's who, what, when, where. All right. Well, where did this fact happen? When did this fact happen? And then these are kind of like, what was it? So what was the thing it happened on? How did you classify the product, or how did you classify the thing? And then this is another way to sort of think about either where or what. So the SQL is really simple, but this is the basic idea, is that there's a few columns about a fact, whether it's a metric or an event, and then foreign keys to tables to tell you how to position that in various dimensions like space and time, product category, corporate organization. This image is from lecture 4. So sorry, from the last lecture. So I just repeated this image from the last lecture. This is a simple quote I pulled down from Wikipedia explaining what a star schema is. So you don't really need to go into that. This stuff in boldface is actually from the formulation of the question. So if you go back and look at the problem definition, the two most important facts for the fact table are a rental and a corresponding payment. I told you what basically was going to be in the fact table. And so if you go and take a look at what's in the rental table, it's a unique ID for the rental event. When did the rental happen? The inventory ID, basically you can think about this as the ID of the movie that was rented. Like what's the ID I used to track this movie in my inventory database? What's the ID of the customer? So which customer did this? When did they return it? When did they rent it? Which staff member did it? And when was this record as a whole last updated? So that's the rental table. Payment table, similar. Every payment record's got a unique ID. It refers to the customer that made the payment, the staff member to whom the payment was made, the rental transaction, the rental record that this applies to, how much the person paid, when they paid, and when was this record in here last updated. So the join column on this table is clearly rental ID. So the join column on this table is clearly rental ID. And this is basically sort of what I came down with, is I picked rental ID, customer ID, inventory ID. So what was the rental event? Who was the customer? What did they rent? Who sold it? Right? What is the corresponding payment record? How much did they pay? When did they rent? When did they return? And when did the payment happen? So that's what I decided to put in the fact table, and you get that from joining rental and payment on rental ID. And so this is what my fact table looks like. This identifies basically the rental transaction, customer, what did they rent, who rented it to them, how do I find the payment event, how much did they pay, and then when did things occur. So the fact is basically customer X rented movie Y from staff member Z at store P on date D, returning on D2 and paying on D3. It's kind of the fact. You could argue that there's actually several facts, like when did the payment happen? It could be a different staff member got the payment, and that would be the case in a real schema, but this isn't a real schema. So we're just going to kind of compress it. But yeah, there are actually several facts in here, and you would normalize it more in a more complicated environment. But for this one, this is just basically the statement of the fact. So I create a table to that effect. So all I did is create table rental payment facts as the select statement I just ran. It's about 16,000 facts. You go take a look at them, and that's my fact table. So I'll just take a pause here so people can take their family photograph, and then I'll move on. But this is what creates the rental fact table that I did, and then this is just something that that shows the first 10 facts in the table. All right, and that's just how many of them there are. Dimensions. This is an explanation of dimensions. The easiest way to think about it is who, what, when kind of things. So in this database, we clearly have at least a date time dimension. Things happened at a date and time. And we actually have location, two different location dimensions, where the person resides and where the store is. So in theory, a person could have rented something from any store. Now, this chain has two stores, so this is not physically a particularly interesting dimension, but there's really two parts to location, like where's the person and where's the store. So you could ask questions like how many people who live in Boston rented a video in New York? So there's really two dimensions to that event. Like where's the customer from and where the event happened. So I decided I was going to do two dimensions of where. So we'll take a look at the customer aspect of it. So this just basically selects the customer ID, first name, last name, and then joins it with the address and the address ID. Customer ID, first name, last name, street address 1, street address 2, district, which is a generalization of the concept of state, an ID for the city, and a postal code. In a real system, there would also be an ID foreign key relationship to the district or state. I don't know why in this one they used pros for districts, but numbers, unique IDs for cities. I don't know why they did that. In a real system, they would have used it for the districts also. We can do a little bit better than this. For example, there is a name for the city in a different table. So there's a table that maps city ID to city. And there's also a corresponding one that maps country ID to country name. And I don't really think we need to go down below the granularity of a city. So, I'm not sure we need to go down to a street number or a postal district. So I'm going to only look at country, district, and city. So I get tired of constantly typing the prefix in. So I basically changed my default schema to Sequila 2. And this query is the query that pulls together the customer location dimension. So I'm going to select the customer ID, first name, last name, the 2 lines of the address, the district, the city ID, and the postal code from customer joining address on customer address ID equal address.address ID. But I'm also going to do some subqueries. I just don't want just the city ID. So I'm going to go look the city up in the city table where the city ID is what the city ID that's in the address. I'm going to go get the country ID, which is in the city table where the city record meets the address. And then I'm going to do an even more complicated one, which is I'm going to take the country ID that I can find in the city table that I can find from the city ID and use that to look up the country name. So there's 3 subqueries in here. This is kind of inefficient. If there were a huge amount of data, you wouldn't really do this because you're kind of hiding joins inside subqueries. But there's not a lot of data, and I don't like doing joins. They annoy me to no end, so I just did these subqueries. But with a little bit of work, this is what you get. Customer ID, first name, last name, the 2 address elements, district, city ID, postal code, city name, country ID, country. So I'm just going to pause here so we can take family photos again. And then I'll move on. I don't want to worry about street or postal code. So I'm going to do basically, I'm going to clean this up a little bit. So I'm not going to pick everything. So what my table is actually going to be is customer ID, first name, last name, city ID, city name, district, country ID, country. And so that's going to be the information is about a customer and their address. So I'm just going to pause here for a sec. You can do a similar analysis for stores. So select staff ID, store ID, city, get the city name, district, get the country ID, get the country name from staff join address, and then you actually have to go through the store table to get the store ID to do the join, etc. But with a little bit of work, you can produce this: staff, store, city ID, city name, district, country, ID country. So this video chain is a store in Canada and Australia, but seems to do like a fair bit of business, with Greece and Myanmar and a bunch of other stuff. So I think when they were doing this sample, they just sort of lost enthusiasm. So they've got a relatively rich model of customers and where they live, but they just kind of seemed to lose their enthusiasm when it came to putting stores in places. So it's not a particularly deep, there's not a lot of data points in this dimension, but we're focusing on the concept, not the actual data. And maybe if we're so successful in our data science that we'll expand and open hundreds of stores. So we now have 2 dimensions. A customer location dimension and a staff store location dimension. Dimensions, when you go and take a basic look at, let's go see if I can find this thing. It's not this one. Star dimensions of a lab book. No, that's not it. Basically, when you do OLAP, there are dimensions, but dimensions have hierarchies. So dimensions often share hierarchies. And what's actually going on with the addresses, the customer address and the store address, is that they share a hierarchy. So at the bottom, they have customer and store, but above that, there's a hierarchy, which is the actual thing we think of as an address. So what I actually decided to do is I was going to go create an address hierarchy. And so what I do is I basically say create table address hierarchy as, and I get the address ID, the city name, the district, the country ID, and the country name, using the same concept of like joins and subqueries. And so if I go take a look at it, this is my address hierarchy. So each address appears exactly once. And then the customer address hierarchy references this through a foreign key. And the same thing in the staff store. And you'll see a diagram of that in a minute, but there's shared hierarchy, and then the actual 2 dimensions kind of pull this in. So that's the address hierarchy. And then I basically go and create the customer and the staff store. So that's the kind of the staff store customer. So customer address ID, city ID, blah, blah, blah. And then I do the same thing for staff store, address ID, city ID. Again, this is not a dimension with a lot of instances, but it's the concept. So there's a diagram later on that'll make this a little bit more clear, but those are the 2 dimensions of location. Date dimension. Again, you can really think about this as there's several dimensions. There's the rental, when was it rented, when was it paid, etc. And then these would share a hierarchy, and the hierarchy would be year, quarter, month, day of month. So there's a chat question. Oh, yeah, I don't see that glowing red thing. Okay, good point. All right, I'm recording. So that should finish it. Yeah, so I'm recording now. People will have to catch up. So the hierarchy is going to be year, quarter, month, day a month. So how are we going to get this hierarchy? Well, if you go back and you look, like select rental date, if you go look at rental and you just select the date, that's the rental date. but there's a bunch of stuff encoded in this. And so what I basically do is I say select rental date as date, then the year of that is year, the ceiling of the month divided by 4 is the quarter, the month as the month, and the day of the month is the day of the month. You kind of run this statement, this is what you get. Date, year, quarter, month, day, a month. So what I'm going to do is I'm going to go make a date dimension. So I'm going to drop the table if it exists, and then I'm going to go create the date dimension. So I'm going to start with the rental information. Now remember, every date I have in the fact table has to reference a date in the dimension table. And so what I'm going to start with is I'm just going to get the dates that exist out of the rental fact table. I'm going to start with the rental date. So I say, give me the date, year, quarter, month, and day a month. So I create the table and select it. Now I go in and change the date, which actually is a really crappy name for a column because it's also a function name, but I'm lazy. Same thing with year. So I'm going to go basically make that the primary key because I only care about dates. I don't care about hours. And so something that uniquely identifies an entry in this date table is the date. I could have used an auto increment or something else, but like I said, I'm lazy. So I go make that the foreign key. So now I'm going to go make sure that there's a second set of dates in here, which are the payment dates. So I'm going to do the same thing. Return dates. I'm going to go into the rental table and get all the return dates and then insert them in. This is where I tried to do the union before and kind of messed up. And in hindsight, even a union wasn't the right way to do it. So there's this keyword in the insert select statement called ignore. You can which basically says, if this is a duplicate, if this would create a duplicate key, just ignore it. And that triggers a warning. If you don't have the ignore keyword and it detects a duplicate key, it aborts the entire insert. So if you're inserting 1,000 records and you've inserted 998 of them, and the 999th one would cause a duplicate key, it aborts the transaction that does all the inserts. There's also an on duplicate clause. So if you're doing an insert select and there's a duplicate, you can specify what behavior you want done when there's a duplicate. But I didn't really want to worry about that. I just want to ignore it. So what happens is this select runs and then it tries to insert all the records, but whenever it encounters a duplicate key, it just ignores it. And you can see I get a bunch of warnings. You can suppress these things so you don't see them, but the connection library we have just prints them out. But these were all the duplicates that I had that didn't get inserted. The table still got updated. It just warned me that it didn't do those. And I did a little bit more analysis. And so if you select count from payment, where the date of the payment date is not already in the date dimension, there aren't any. So I don't actually need to do any inserts from payments because I've covered all the dates. I'd add them if I had them, but I don't, so I'm not going to. But anyway, go back and share the family table of kind of creating and loading the data into the date dimension. Does somebody have a question, or was somebody just waving? All right, I'm going to go with no questions. All right, so now if you think about it, when I did the fact table, actually all the dates are date and time, but I'm only linking them to time. Sorry, to date. I'm not worrying about the time. So the next thing I do, could I please go over the customer hierarchy table once again? Customer hierarchy table. Yeah. here's the easiest way to think about it. I'll skip the diagram. All right. There is customer. So there's really two. I mean, I wouldn't call it the customer hierarchy. What's happening is there are two location dimensions. So if you think about this fact that a rental occurred, and you ask where, the where question for this rental, it's a little ambiguous. Are you asking where does the customer come from? Or are you asking where the store is? Now, context would tend to make you think it was the store, but it might be a meaningful question to ask, please show me the total dollar value of rentals from customers who live in Boston, regardless of where they rented it. And so what happens is you start with this location dimension, city, district, country. And then the customer record, if you go basically to go in and take a look at customer. So if you go take a look at customer, you can see that the customer's got an address. If you go look at store, the store's got an address. And so when I did that kind of probing, I came to realize that there's a common concept of an address, and then this gets attached to a customer or a store. So this is one dimension, the staff, store, location, and this is the other one, the customer. They just happen to share a hierarchy. And so what I did is I said, okay, I'm going to make an address dimension, an address hierarchy. So if you go take a look, there's an address table. So that's the address table, but you'll notice a couple of things that are weird about this. It's got the city ID, but it doesn't have the city name, and you don't know what country it's in. To get the city name, you have to go to the city table. So that'll take a city ID and convert it to a city name, and it'll tell you what country it's in. So then you got to go to the country. You go take a look at that. So that gives you the country ID and the country name. So to actually get an address, you basically have to start with an address. That's going to give you a city ID, which allows you to find that. In there is a country ID, which allows you to find that. So I wrote, there's a little bit of SQL magic that says, okay, take this table, and that table, and kind of pull the core information together to give you a single table with this information in it. And that is this statement up here. All right, so that's so this is creating the address hierarchy. This is the shared hierarchy between the two dimensions. So I want the address ID, I want the city ID, I want the city name, I want the district, I want the country ID, but that's not in the address table. So what I have to do is I have to take the city ID from the address table and use that to find something in the city table. This is like subquery 101. And then get the country ID. So I'm going to say, I have an address ID. I have a city ID for this address record. Go find the corresponding city record and get the country ID from that. And that'll give me the country ID. And then I've got to do that a little more deeply, which is I've got to go to the country table and then select the country name from the country table, where the country table's ID is the one I just found the other way as country. And so with a little bit of SQL magic, you wind up with this. So that's the shared address hierarchy. The dimensions are just joining customer with that on address ID, and then joining staff and store on that with address ID. And so going down to the diagram, this is what's actually happening. is that's the address hierarchy. This is the customer address dimension. And this is the staff store address dimension. And so that's how those two dimensions got made with a shared hierarchy. And then this is the date dimension. And so I need an entry in the dimension table for every fact. And so I basically just need to go through and make sure that for every date and every address I have somewhere, I'll put a corresponding entry in the dimensions table when I built it. So that's how I got those two dimensions. So back up to where, anyway, so I'm now going to go back and say, okay, I got to go kind of modify the fact table again. Because like I said, I originally had date times. So I had to do a little bit of work. So I took the existing names, rental date, return date, and payment date, and changed them to, date times. And then I went in and I changed their names, you can see. So I changed it from rental date to rental date time. Those are going to be the timestamps, so the day, hour, minute. These ones are going to be just the dates. So I went back and added a column, rental date, payment date, return date. They're dates, not date times, and this is where they go. And then I went in and said, update rental payment facts, set the rental date to the date part of rental date time, the return date to the date part of return date time, and the payment date to the date part of payment date time. And when you go take a look at that query, this is kind of what you get. Rental ID, customer ID, inventory ID, staff ID, payment ID, amount, the date times, but then just the date versions of these things. Now, I could have always gotten these values by just applying the date operator to these date times, but because dates are what I'm using as identifiers or keys in the date dimension, I need to have foreign keys, so I want just the date. So this is going to wind up, each of these is going to wind up being a foreign key into the date dimension. So that's what my rental fact finally looks like. Now, in a real star schema, there are lots and lots of other dimensions. An extremely common one is, where does the product that was purchased fit into some kind of classification of products? Amazon has an API for querying information like sales information, that kind of thing, about things that were sold through Amazon or the Amazon marketplace. And it's hierarchical, right? So you can sort of say, all right, shoes, women's shoes, where do you go? And so they've got a relatively rich hierarchy of products. This kind of exists in the classic cars database, although it's not very deep. So this product line, and then within a product line, this product scale. If you go and you look in Sequila, so if you go take a look at the Sequila schema, let's see whether I can find it. This one's as good a one as any. You can basically see that this is a film. So this is the thing that's referenced by inventory. So inventory, film, they have categories and they have languages. So in theory, you could sort of ask questions about categories and languages, but these are not really hierarchical. So if you go back and take a look, it's not like they've got a deep hierarchy like Amazon does, where they say like this movie is, fiction, it's historical fiction, it's English historical fiction. It's just a bunch of tag words. And so I mean, you could use it as dimensions, but it was kind of weird. I actually tried that, but it looked a little weird. So I just decided I wasn't going to worry about this. In a more complicated environment, like a bigger environment, you typically do have product categories and classifications, but I could not find one that made sense. So I just decided to ignore that. But that is probably, in addition to time and location, position in a product taxonomy is probably the third most common dimension, but I just couldn't find one that I liked here. And so because of that, I just decided to ignore that particular part of it. And then we'll go back here. So that's just kind of as an aside why I don't have a classification of the films. It's such a common approach or common concept that when I've asked students to do something like this with Sakila in the past, they always try and do it in classifying the movies. And I just wanted to make it clear that it's just not worth it for this one because it looks kind of weird when you're done. So with a little bit more work, big picture. The customer location dimension, the primary key is the customer. The staff store location dimension, the primary key is the staff ID. You can think about that as the primary key is always the root thing. Like this customer is what identifies it, and then I go up. So the staff is the unique thing. So I just went in and added those as primary keys. I went in and I created a bunch of foreign key relationships. So the dates in the fact table are foreign keys in the date dimension, and the customer and staff IDs are the foreign keys into the location dimensions. This diagram I already kind of showed you. If you take a step back, this is what it looks like, which is there's facts. Right? These endings are wrong. I kind of messed this up, to be honest with you. Actually, I'm not sure I did mess it up. But anyway, if I have a fact, I can find the customer address. If I have a fact, I can find the store address. And if I have a fact, I can find the time, where it is in the date time space. So that it's not a very interesting star, but it's simple and it kind of illustrates the concepts. After I've run all of those SQL statements, let me scale this down a little bit. This is the schema that I get, which is rental payment fact. That should actually be 0. The way I built it, it isn't, but rental payment fact over to the staff. So that's the staff store dimension. Because I wanted performance, you can see that this is actually denormalized. I should act in a normalized schema. I would actually not put all this address information in this table. I would just use the address ID and join. But since I'm focusing on performance, I kind of did not denormalize. I denormalized here. And so there's a functional dependency. An address ID always uniquely determines those. So if I were going to normalize the table, I would have to decompose it here. So that's how I find the staff store from a foreign key, customer from a foreign key, and then there's 3 foreign keys from the fact into the date and time table. All right, so I'm going to pause just so you can take the family photograph. But that's basically my star schema. It's not the world's most interesting star schema, but it does explain all the concepts, and it is, I mean, I could have given you a much, much more realistic one, but these things are tedious, as you can see, to build. There's a lot of like moving data, cleaning data, weird uses of insert on duplicate, that kind of thing. And so I wanted you to understand the star schema concept as opposed to understanding all the weird things you can do with SQL to get the data cleaned up. All right. Operations. I asked you to do 3 operations. Roll up, slice, and dice. There's also a drill down. So Um, this article on Wikipedia is pretty good. There's a lot of articles about the various operations. So slice, sorry, a roll up. A roll up involves summarizing the data along a dimension or one or more dimensions. My slice is, sorry, my roll up is I want to know all the rentals and the total revenue by year and quarter. So I'm slicing the data and rolling up along that. So basically, in 2005 in the second quarter, 2006 in the first quarter, this is how much I rented, that's how much I sold. So you can see basically I'm going to do the aggregate operators. I'm going to pick the year and the quarter. I'm going to join the facts with the date, and then I'm going to group by the year and the quarter. And so that would be an example of a roll-up. You're taking a cluster of cubes and kind of compressing them into one. A slice is just looking along one dimension. So I'm going to say I want to see all the facts. So please show me everything I rented in the United States. So select the rental ID, the amount. From facts, join the customer location on customer ID, United States. If I wanted to, I could then aggregate it, but technically you're slicing. Normally, when they're base facts like this, you don't ever just slice them. You would also roll them up, but this is an example of a slice. And then a dice is just basically sort of a slice in multiple dimensions. So what I'm really saying here is go show me everything I rented in the to a customer who lives in the United States in the year 2005. And so you can see up here. And so these are all the events, all the things in the fact table that occur like in the intersection of that date and location. And so that is the star schema. So I'm going to pause for a minute. You can send me a chat message if you want me to go back over anything or scroll again so that you can take another photo. So I'm just going to pause for a second. All right, I'm going to go with silence equals consent on this one. So I'm going to assume you've had all your photographs. All right. Graph versus relational database. I wanted you to basically kind of understand the core distinction between a graph database and the relational data model. And so I simplified it down because by this point, this exam has becoming progressively, a lot of coding and relatively detailed stuff. So write a Cipher query that shows all nodes and relationships with a path length 2 or less, starting at nodes that are fans and ending at nodes that are teams. So I kind of have to play with these things even when I do them. So let me go see what I can find. That's not it. So we'll go get the actual answer. All right, so that's the graph database one. Star schema. Don't know why I didn't do that one. Must be one of the other ones. Nope. So let's go back and take a look at this. Show all nodes and relationships with a path length 2 or less, starting at nodes that are fans and ending in nodes that are teams. So we're going to do this the old-fashioned way, and we'll actually write it just in time. I don't like doing this because sometimes I have to tinker with it. And so you get a bit of, you're trying to think about explaining it while you're writing the query. It can get kind of awkward, but we'll give it a try. All right. Pick a project. I guess this one will do. So I'm just going to start my graph. Come on. All right, we'll connect to my graph. So basically, I want to match something. I want to start with a node, and I said that node has to be fan and ends at a team. So I'm going to go back in here. It's going to start at a fan. And so it starts at a fan. This one could be star ... 2, which means I want that to be 2 or less. I'm sorry, that starts as this. And it ends at a fan. No, it ends at a team. So I want a path where the ending node is a team, the starting node is a fan, and there's at most 2 things in between, 2 relationships in between. So we're just going to say P is going to equal that, return P. And so that's the answer, which is every path of length 2 or less, right, that starts at a fan and ends at a team. So you can see, if you go look at these things, and so those are all the paths that start at a fan and end at a team. It's a relatively straightforward thing to do. I had planned to ask you to do the corresponding joins in the layman database, but anytime you cross a link, it's a join. So
dbms.security.crete user
username, so you get to a fan
password
through teams and things.
require
it's almost
password
impossible
change
to do a query like this in the relational model, but I just decided not to ask you to do it. But that's a real simple query. So I want a path. The path starts at a fan, ends at a team. I don't care what's in between it, as long as it's less than 2. And so that's the query that gives you the answer. So I'll just pause there for a second. All right, so I'm going to assume we took the pictures. And then I asked you to go back and define a data model that would support fan, comment on, comment by, supports, follows, and team. Right. So basically, I asked you to take go recreate this kind of model, but do it in relational. The natural inclination on this is I'm going to have a table for each of these types. I'm going to have a table for fan, table for team, and then for each one of these relationships, I'm going to have an associative table, an associative entity. So these would be join tables. And these would be, so these would be the two tables, fan and teams. And then these would be the associative entities, the join teams. I would have accepted it if you had done that. There is an implied issue with this, however, in the sense that these are not strongly typed. And so I can basically just go in here and say match F fan where first name equals James, return F, where F dot first name. All right, so that gives me James Madison. There's nothing that stops me from doing this. So now I've added a property just to that instance. Perfectly valid thing to do in a graph. To support that in relational, you would have to go back and alter a table and add the column to fan. And so if you went back and altered the table and added the wife column, I would go back and say match fan, first name is equal to George, set F dot tooth kind equal to wooden. And I would keep doing that. And so you can see that if you look at this, they're all different. It's not really tabular data. So they don't necessarily all have the same attributes. So I would have accepted it if you'd done it as a fan table. Similar argument applies to the relationships. Right? If I basically went in and follows, right? So I'm just going to go here and return R. Just going to get back the relationships. They don't have any properties, but they could. Like, when did they start following this person? How many times, have they looked? And so the relationships are also not strongly typed. But the real thing here is fan. And so these are not strongly typed. And the labels don't need to be distinct. Sometimes you have graphs and you have edges. So if you go back in here and you think about my other example, I've got players and I've got fans. What am I going to do? Somebody's a fan and a player, right? People are in here to be fan, player, and somebody could be a fan, a player, and a writer. And so the relational model doesn't really handle graph data particularly well. And so the trick to this one was actually just kind of going and understanding. That's not it. All right, so what I actually did is this. No, that created a new one. So I'm going to kind of scroll in here. Where's the Zoom thing? So in essence, what's happened here is I have a table of thing. Thing has got an ID. It's just a generated ID. Things got a kind. The kind is an enum. It's either a node or a relationship. If it's a relationship, it links to other things, the source of the relationship and the target. You can't really do these endings properly because if I'm a node, these both have to be null because nodes don't link things. If this is a relationship, neither of these can be null, and they both have to reference another thing. So you can't really draw this properly, but the net of it is that I've got a single table, which is what kind of thing is it? So what's the idea of the thing? What kind of thing is it? And is it connected to two other things? And then I've got a separate table of labels. So labels have a unique ID. They have the thing for which they're a label, and then the actual text of the label. And the same thing with properties. Every property's got a unique ID. Property applies to a thing, and then it's got a name. What's the name of the property and the value? And I said that the values could be text. So at their heart, graph databases, this is kind of the nucleus of what goes on in a graph database, is this concept. So if you go back and take a look at my database has the following. So I'm going to go back in and take a look at, I've got labels, I've got things, and I've got properties. So I go basically take a look, close other tabs, close this one. I'm going to go look at my things. So these are all the things that I have. See, most of them are nodes, but if it's a relationship, right, it's got the IDs done. So what's the ID of the thing? What kind of thing is it? And does it link to other things? This is my label table. So what's the unique ID for this label? What thing, to which thing does it apply? And what's the text of the label? Right. And then in here, the similar thing for properties. And so these are the properties. Now you can see what's been going on here. If you look, you can see that I've actually been adding the graph database. So you can see that there's a thing in here, thing 105. It's got a team ID BAL and it's got a team name Baltimore. And then if you go farther down here, you can see that there's a thing 3192. This is the player ID. That's the last name. That's the first name. And so this is how I would have done it. Now, I would have accepted it if you'd done tables, but then I would have pointed out in the comments that I gave to you that because these things are not strongly typed, anytime I added a property, you'd have to go run an alter table. So you do it this way. And then I've written a bunch of code to manipulate this. And I'll kind of just show you some of that code. I kind of de-emphasized all of it and just asked you to do the schema. But this is how I would have implemented some of the operations. So let's just this all load. I guess strike here. Don't need homework 2. All right. So just trying to remember which one. That's homework 4. This is going to be on the finals. All right. So I basically wrote a file. It's going to compress this stuff. So there's a bunch of helper functions: get a connection, run a query, match. Those are just relational things. And I built 4 Python classes: a graph class, a node class, and a relationship class. So this sort of mirrors Py2Neo. So we'll just go to node. Node is the simplest one. When you create a node, you give it a list of labels and a list of properties. And so this constructor makes a node object. And there's a toData function, which is basically says, go convert this to JSON. Right? What the heck? So that's all that's in a node. We'll go back and we'll just go take a look at my tests. All right, so we're just going to go and we'll start doing a new set of tests. So we're just going to say def. We'll make this a little bit bigger. Test R1. And I'm going to go say, all right, we'll just go n is equal to relational graph dot relational node. And it's going to take labels. So I'm going to say it's a player and a writer. And it's going to take a bunch of properties. So the uni is 101, and the hat size is going to be 8, because I said they're all going to be text. And then I'm just going to go print n dot toData. And I'll just run test R1. Just going to make sure I commented all of these things out. All right, so we'll go run this one. We'll see what happens. So I got the type is node. I have not set an ID yet because I set the ID in the database. The labels are player and writer, and the properties are the uni's 101 and the hat size is 8. If I want to save it, I basically will then go and say, I'm going to save it. So I'm going to go save n. And I'll run this thing again. And you can see that it now has an ID because I compute the ID when I put it in the database. So if I go back in here, it'll all be linked together. So the ID is 3193. I created a view just for the heck of it called labels and properties. And so what I'm going to say is where the thing ID 3193. I go run that. And so you can see that it basically joins thing, property, and label. So 3193 is a player and a writer. The uni's 101, the hat size is 8. So that kind of just pulls it all together. It's not particularly well normalized because I'm kind of joining, so I know I get more than I want, but I can use this to query. So if I wanted to find all the things, where label is equal to write as player, that's going to return everything that's got the player label. right? So in essence, I query the labels and the things, it returns the thing ID, and then I use that to hydrate stuff. And so you can go back and take a look at the code. I'm not going to go through it in too much detail. Relationships pretty much the same way. It's got a start node, labels, properties, and an end node, and then it dumps itself to data. All the work's done in here. So this will save something. So you gave me a thing to save. I'm going to go get a connection to the database. I'm going to create a cursor. If the thing's a node, I'm going to insert into the thing table the kind. So I'm going to go run that. Otherwise, if it is a relationship, I'm going to insert into the thing table the kind, the source, and the target. So for a thing, the only thing I put in the thing table is it's a node. For relationships, I have to put the node at the two endpoints and then do that. And then I go and say, what's the biggest thing ID? Well, that's clearly the one I just created since I did a transaction. And so now I know what the ID of the thing is. And so I go set that value. And then I could basically go and say, for every label, go put an entry in the label table. For every property, go put an entry in the property table. And so if you give me a node or a relationship, that's how I save it. This will load a node. So if you give me a node ID, I go label and property, and I find the thing ID. And then I just basically get the properties and the labels. I do a little bit of work to convert the table structures into JSON. And then there's a match operation, which if you give me a set of labels and a template, I'll return, possibly a start and a node end, I will return the match. And so this is a simple, I'm going to give you this code so you don't have to do it. But basically, that was the thing that I was looking for, is this is the nucleus of a graph database. And so the answer to the last part of it was going to be just that diagram. So I said, like, in your, define a data model that would support blah, 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 blah. You can just provide the ER diagram. You don't actually have to do it. When I give you the answer, I'll give you a link to this in the GitHub project and actually the definitions. But the net of it is, I didn't really expect anybody to get this one because it's really counterintuitive. But that's the thing I was looking for, and then the operations to manipulate it. So that's the answer to the graph question. And then I'll give you some code later on that shows you how to do the match operations against this. So that is the question about graph. All right, so I've done question 9 and question 10. I'm going to pause for a second. And then we can use chat messages to determine if there's anything else people want me to cover. So, all right, so, all right, so, all right, so confused. Are we supposed to provide? No. So the answer is for question 10, you don't have to provide the code. I'm just went through the code to give you an example of what it's like. You just have to do this basically, and then the cipher statement that I showed you previously. 3.6. So question 3.6. Let's go find section 3.6. So I'm trying to remember what these things are at this point. 3.6. All right, 3.6. implement the faculty-student model, faculty-student advisors model in a graph database. All right. The graph way of doing this is significantly different from the relational way. When you do types in a relational database, it's based around tables. So the table the tuple is in determines its type. A graph database is not typed. There are nodes. Nodes can have arbitrary sets of properties. How you type a node is you put a label on it. So if you take a look here, this one has been selected. This node is of two types, person and faculty. This one is of type student. And so instead of thinking in this in terms of tables, I've got to put part of it in one table and part of it in the other table. You have a node. The node's got the properties that are associated with that node. And if you want to type it, you give it a label. This is a standard pattern, but instead of sort of saying I'm gonna split these things into different tables, well, I've got a node. I'm gonna make it a node, and if I want to classify it, I'm going to go and say, what label does it have? And so the answer to this is, if you go back in here, and I just go over here and do match, P colon faculty, return P. Oops, wrong database, I guess. Yeah, I've got like 9 of these databases, so must not be in this one. Let's go stop this database. Maybe it's in this one. But we'll go back and take a look at the code. And so, is this it? Right. So it is. So I asked you to do a bunch of methods. So a bunch of this stuff up here are just helper methods. I pulled these directly out of the helper code that I gave you for homework 4. So the first thing is to create a faculty. Well, this is running in the graph. So the faculty's got a last name, a first name, an email, and a title. Right. So I'm going to go and compute what the next uni is, right? So the first thing I'm going to do is I'm going to create the prefix. So there's a standard function here that says go get the first 2 characters of the last name, go get the first 2 characters of the first name, concatenate them together. So in my case, that would be FED0. I'm going to begin a transaction. I'm not going to auto commit. So when auto commit is turned on when you're connected to a database, every operation commits when you're done. And I don't want to do that. So what I'm going to do is I'm going to say, my first query is match across all people where their uni starts with something and return the count of those. So in the same way you've got that weird %s behavior when you're using PyMySQL or the Python connector to MySQL, putting something in curly brackets like this is how you put a variable in a query. So what this is basically going to do is if this function returns FED0, this is going to count all the nodes whose uni property starts with FED0 and return it. And then as count, I'm going to add 1 to that. So now this is the 2,713th person. I'm going to go make a node. So I'm using the Pi2 Neo and the stuff I said, make a node. The labels are person and faculty, and these are the properties. So go make that node, create it, and commit. So that's create faculty. Just pause here for a second. Get faculty. You can reuse the find nodes by template that I gave you from homework 4. So what I'm saying is, if you want to find a faculty by the uni, the type you're looking for is faculty, and the template is the uni's this. Return it. Create student is almost exactly the same. Last name, first name, email, major, advisor. I'm going to go compute the uni prefix, run the query again to figure out what the right number is. All right, so now I know the uni to assign to this student. You gave me the advisor's uni. I'm going to go get that node based on that uni. If it doesn't exist, that's an error. Now, there's a way to define constraints like this in Neo4j, but I didn't want to go through it. So I actually wanted to make this part explicit, which is you gave me a uni. If I can't find a node of type faculty with that uni, it's an error. If I can, we're good. And so when I get to this point, I know that I've computed a uni, so I can make the node, and I've found the advisor. So I go in and say I'm going to make a node. The node is person and student. These are the properties. I'm going to go create that. So now I've made the node. Then I'm going to say I'm also going to make a relationship. F is the faculty I found. Advises, student is the student I just found. Go create that relationship and commit. And then get person. Well, all I really do is I just have a list of the fields that are specific to person. And so if you ask for person in a uni, I go and do a find everything that's got the label person with this uni, but then I just don't return the keys, the properties that are not in this list of things that make a person up. So kind of the way to think about this is that this is like the one table solution for inheritance. And this is how you do the view. And so that gets person, that gets student. And then these are some tests that ran. And so this is going to create a faculty member, etc. I'll kind of comment these things out and see whether I can actually find. I'm not sure if I got like 3 databases on this system right now. So let's go see. Okay, DB host, DB user. So let's go take a look at this. And it started. We'll try and connect. And this one doesn't have it in it either, which is not good. So then we're going to stop this one. Yeah, screw it. We'll just use this one. So this one has got, just gonna make sure it's got DB user. Let's go admin, add a user. So I'm gonna go get this thing, DB user. It's gonna be an admin. Set the password to DB user. I'm gonna go add that user. All right, so it already exists. That's a good sign. So you can see that I don't have any of these things here, so now I'm going to go try and run these tests. So I'll go back in here and I'm going to go run this. All right, so there's a bunch of print messages here, but I'll go back into my graph database. Close this and open it. Sometimes it takes a minute to refresh. So you can see it just kind of jiggled. So now I have student and faculty. If I click on that, you can see that it has the node that I just made. All right, if I go and expand this, you can see that it's got an advisor's relationship to that person who's Bilbo Baggins. So Bilbo has got two labels, person and student, and those are their properties. FED0 has got two labels, faculty and person, and those are the properties. And so that's the code that I just went through here. It's just that bunch of stuff. And you can reuse all of the base functions like run match, run queue, find node by template, create faculty. So all of these things actually come from homework 4. These are the ones you have to write. And so if I just wanted to go back in down in here, I'm going to go make another one. So I'm going to go here and go. So basically, I'm going to go say I'm going to go create a student. And the student is going to be Frodo Baggins. It's going to be FB at Columbia. His major is going to be, I don't know, magic, and his advisor's FED0. I'll just go run this thing again. And then if I go back in here and I go run this again, that's FED0. I expand it. You can now see, and I'm going to click on this. So type faculty and person. It advises two things. That's person and student. That's person and student. So that's all you really need to do. So I'll just go back through so you can kind of take the family photos again real quick. This is reusing the code from homework 4, so that's just creating the connection to the graph. This code just computes a uni prefix. So if I give you a last name and a first name, what are the first two characters of the last name? What are the first two characters of the first name? Concatenate them and return the result. To create a faculty, you compute a uni prefix, convert it to lowercase because text comparison in Neo4j is case sensitive, unlike MySQL, so I lowercase it. I begin a transaction without auto commit because I have to do several things. I run this query. So if I come back into my graph database and I go run this, but I'm going to go try something else. I'm just going to go with player, where the p.player ID starts with, and we'll just go ORT, and we're just going to basically go and we're going to return P. You can see that all of these guys, player ID starts with ORT. And if I just return the count, that's going to tell me how many of them are. So the answer is 7. So if I just apply that or person, uni, and starts with, I don't know, F-E-D-O. There's only one uni. And so that's how I basically go and compute the uni from the code. Now, the reason I have a transaction is I counted something and I'm going to insert something based on that count. I can't have anybody else count something and insert. So I'm just trying to like prevent this bad things from happening. So I compute the uni, I make the person and the faculty, and then I just commit. Get faculty does the match by template, which was a helper function that I gave you previously that just basically forms calls a Py2 Neo match statement. So that's kind of create faculty and get faculty. And that's create student. It's pretty much the same thing, and get students, get person's pretty much the same thing. And so that's the code for get person. All right, so that's 3.6. 3.4. So we went over 3.6 twice. All right. So so now there's a general consensus to go over 3.4. So let's go find 3.4. Remember which one 3.4 is? Yeah. Oh yeah. That's 3.3. That's 3.4. Schema refinement and improvement. So I told you to only worry about order details and products. Told you not to worry about any of the other ones. And these are the schema that come with it. So you can see they're already not null. What would I do here? There's a couple of things that I would do here. So let's go take a look at it in the database. So we'll go take a look at classic cars. That's classic cars. And I said, just close all of these. Order details. Set order details. So let's take a look at this, and then we'll go take a look at the table. All right. So a couple of things here. Probably should have a primary key. So the primary key for this is the order number and the order line number. So that'd be the first change I would make, is I'd give it a primary key. So that's something that's obvious, is to just go give that a primary key. I'm not going to worry about that right now. They're all not null, which is good. So let's go back and take a look at this. A couple other things I would do here. Well, product code is clearly a foreign key into products. So that's the product code. So the next thing I would do in here is, in addition to that, I would go in and add a foreign key. That's going to be classic car order details. It's going to reference, products. And the product code is going to reference the product code. So I would go and create that foreign key. Now I'd have to go back and make sure that in products, I also made that a primary key. But clearly, if you think about this, you go back and take a look at it. Order details should have a primary key. Products should have a primary key. And there's a foreign key constraint between order details, product, and product code and product.product code. So those are just some key cleanups that I would have done. So we'll just go apply that. Well, I don't want to apply this in case I have to do, well, too late, I applied it. So I'm going to close that. Go and apply this. All right, so now I've done the primary keys and the foreign keys. Let's go take a look at this data. Right. Those are already numbers, int and decimal, and they can't be null, which is good, but presumably they can't also be negative. So I'm assuming that quantity ordered minus 17 is not a valid value for quantity ordered. And so what I would do at this point is I would go in and say, alter the table again. Let's just close all of these out. Let me go and alter the table again. Alter the table again. So I've got the primary key. I've got the foreign key. I'm now going to go add a trigger. I said in the text you might need to write a trigger. I said you would only need to do it for insert. So I'm going to go back in here and I'm going to say, okay, I'm going to go create a before insert trigger. Let's go see whether we can make this thing any bigger. All right, and the rule here is if new dot quantity ordered less than or equal to 0, then signal, make this bigger, signal SQL state, 05001 set, now there's no colon in this language, set message text, is this a quote? Never remember the syntax of this damn thing. Set signals, set SQL state. What the hell is the damn? Set. What is it not like here? All right, signal SQL. All right. Signal, no parentheses. Signal SQL state. SQL state. And we're going to call it 50. Set message text equal. All right, here we go. So if the quantity ordered is less than 1,000, boom. Seriously, quantity must be positive. Do the same thing here. And it is called price each. We'll just call this 501. Seriously, free. And so that is a trigger. Now, there's no check constraints in this database, so you use a trigger. So that'd be an example of just what I'm looking for. Somebody asked a question. If you notice, you sort these things. Order number, order line number, order by. You can see that they actually go like 1, 2, 3, 4, 1, 2, 3. So clearly these things are incremented. If you really wanted to, you could go in and just basically say, you know, declare line count int. Right, then down here you could go select count of star at into next line count from order details where order number is equal to new dot order number. And so what we're going to say here is go count the number of order details entries with this line number. We'll set the next line count. So that's going to increment it. So if I've already got 3, this is the 4. Then it would say set new dot order line number equal to next line count. And so if I've got 3 of them, that'd set it to 4. So that way that would stop somebody from like mistakenly inserting 217 if there was only 3 line items. So that'd be an example of what you could do in this trigger. That's not something you would be able to do with a check constraint. These things are something you could do with a check constraint. There's some other things you could do if you really wanted to kind of get sort of freaky. So if you go look at the products table, all right, so products have a manufactured suggested retail price, but they've got a buy price. So presumably this is the price it costs to sort of wholesale price. What is my cost of goods to get this? So if I really wanted to kind of go wild here, I could say select buy price into base cost from products where products dot product code is equal to new dot product code. It's product code, right? Yeah, product code. So now that's gonna go and figure out what my cost of goods is. And then I would do if buy price is less than new dot price each, then signal SQL state 50502 set message text equal to we are not a charity. And again, this language doesn't use a colon there. And that basically would not allow you to have a price each that was less than the cost of goods acquisition. So, And then there's similar things you could do. So that basically would be a trigger that would go and protect order details. If you go and look at products is actually kind of interesting. There's a couple of things about products. The first one is, if you look at the product scale, so if you do look at select distinct product scale from classic cars products. Oops. What did I do here? Unknown column product scale. So what did I do? Oh, produce scale, product scale. That's clearly an enum. And so what I would do is I would just basically go in and say, look, product scale. Product scale is clearly not just a var car 10. So I would go in and say, look, this is really an enum. And then I would go and add the actual values. So the actual values for the enum would be those scales. So I would go and convert product scale into an enum. That'd be one thing I'd do. You go take a look at a couple of other things in products. Product line would really, that should be a foreign key into product lines, but I told you not to worry about any other tables. It'd be also tempting to say, go convert product vendor into an enum, but that would actually also just kind of weird. So the only things I'd really do on this one is give it a primary key, convert that into an enum, and then just do, you could do the triggers here. Like none of these could be negative. I'd only really care if you kind of did the trigger for one of them. So if you did it for order details, that'd be fine. But those are the only cleanups that I would see for 3.4. All right, so we went over 3.4, 3.6. Can we 3.4 again? Can we go over the 3.5 diagrams? So let's go find the 3.5 diagrams. So I don't even know what the 3.5 diagrams. Oh. All right, so that's the diagram for inheritance. So basically, I think I've actually made a mistake on this one, or I'm not really sure. But basically, there's a person table, so it's uni, last name, first name, email. If you have a faculty, there must be a person. If you have a student, there must be a person. This is optional, and it's actually kind of weird because if you have a person, you don't necessarily have a faculty and you don't necessarily have a student, but you must have one of them. There's no way to express that in relational. So that was the ending that I picked. And then I just manually drew this. So I loaded this into, I think, PowerPoint. So I just took the diagram, loaded it into PowerPoint, drew this arrow to represent the inheritance. But that's the inheritance diagram. If you go down into Neo4j, you just capture the screenshot. So for instance, you can see I selected this one. It's of type faculty and person, and these are the properties. So that would have satisfied for the screenshot. And I did that in Neo4j. The screenshot, the graph for key value. This is what it looks like for Redis. Redis handles taxonomies. It's such a common thing that it's a pattern on the keys. But I don't want you to have to install Redis Commander. So if what you just did was went into applications, utilities, In my case, it's terminal, window, command page. So make the text bigger. If I went Redis CLI, if you just did keys, that would be enough because it's basically the same information. So you can see it says there's a person, student with this uni, there's a person, faculty with that uni, and advises, FED zeros that. If you went and did an HM get, and you did person, student, P0MA2, oops, it's not H, it's got to be H get all. All right, so what am I doing wrong here? Oh, it's POMA2. So that's all the stuff for Ponce, Mary Ponce. And then if you wanted to do, you could basically say, is it L range? I can't remember what it's called anymore. Yeah. So if I did L range, that shows me all the people in the list of people that FED0 advises. So in terms of a diagram, for 3.5, just a screen capture of that would be fine. You don't need to do Redis Commander. And so I think I've answered all the questions. It's been almost 2 hours. Mentions Q9 customer hierarchy. There's one new message. Could you show us the code for 3.5? Okay. You want the diagram and the code? Wow. Right, so let's go find my notebook again. Okay, so that's the shell. Let's go find my notebook again. Is this it? All right, so I'll do the code for 3.5. It's not it. All right, so let's go through the code for 3.5. So 3.5 is SQL. All right. Also, I'll do the code for 3.5, and then I'll wrap up. Just a bunch of stuff, helper code, get new connection. Some of you may have actually experienced an error with this, and I'll explain what the error is, because I think when I wrote the code in a recitation, I got sloppy and made a mistake. It's what happens when you try and rewrite code from your head while people are watching you. But basically, this statement run queue I gave you, it runs a query. It's maybe given a connection, right? I think I actually was supposed to give this thing a cursor. This is not the right one. Yeah, so that is probably the explanation. So I go to 3.5. Because, yeah, I did make a mistake on one of these things. That's not it. It's 3.2. All right, so I've got like 900 of these things. So let's go try and open another one. This 9's already open. All right, so we'll just go back to this one. So in run queue, you can give it connection, the query statement, the arguments. Do you want the answer returned? Do you want to commit? And have I given you a cursor? The database, the transaction manager determines what a transaction is seen based on what the cursor has touched. So if I'm running this query inside a larger transaction, I need to tell this statement which cursor to use. So there's a little logic in here that says when I'm running the query, if I wasn't given a cursor, I'm not part of a larger transaction. Go make a connection and a cursor. Otherwise, use the cursor I was given. So when I get here, I have a cursor. It's either one I created or one I was given. I then run the statement. Maybe I return the data. And I may or may not commit. Was I asked to commit? So if I wasn't asked to commit and you give me a cursor, what I do is not going to get committed and it's going to be part of the bigger transaction. So that's the run queue statement. So now we got to go way back down here. And we got to go through the code for 3.5. So now we're going to go down here. And I cleverly overrode. All right, so I'm basically going to have to go back in and put that cursor stuff in. Not quite sure why I overrode it here. So basically, if cursor is none, CNX is equal to get new connection. And the cursor is CNX cursor. Right. So then I'm going to go get the connection, run it, which is just what I did before. So let's go take a look at creating a faculty. Last name, first name, email, title. I'm going to get a connection and I'm going to get a cursor. And I'm going to set the transaction isolation level to serializable. I'll explain why in a minute. Yeah, I know what the problem was. So I'm going to compute the uni. I'm going to go do the count. So go find all the people that have got that uni, run the query, increment it. I'm basically going to go, and actually, I don't want to do the commit. That actually wasn't the problem because I don't want to commit that. So I'm going to go insert into the person, but I'm going to give it the cursor. And so that way, this request is going to use that a subquery is going to use the cursor. If I don't pass it in, it starts a new request. So the second time I come in, it starts a new request that is considered a different transaction, and it can't see its update. If I commit here and then fail, I'll have created a person, but not a faculty. So I can't commit until I get here. But if I don't use the same cursor, so I wasn't passing the cursor in here, this statement starts a new transaction and it can't read the other transaction's update. And so the only way you can see the uncommitted update is by passing the cursor to both of them. So some of you were having that foreign key problem, and it was because I wasn't passing the cursor in the sample that I did in one of the recitations. And so what I'm saying is that all of these statements happen in the same transaction, and I do that by passing the cursor in. And so that fixes the problem. And I use the isolation level to make sure that I don't miscount the unis. And since I don't commit at the end, I can't get into a situation where I make a person but fail before I make the faculty. I either make all of them or none. And so that's basically the code for creating a faculty. The code for creating a student is the same. And I commit, and then I retrieve a person, I just do the view. So I run these things, right? Non-default argument follows default argument. So that is Q, cursor is equal to none. Run the code. And then I can go create a faculty, and it is going to be Dumbledore, Albus. It's going to be AD at Hogwarts. EDU professor, go around that. Cursor's not defined, so now where did I do this? So what happens if you write code on the fly? Oh, because it's cur, so cursor's cur. Cursor's cur. Cursor's cur. That's student. Cursor's cur. Cursor's cur. Cursor's cur. Go run it. Go run this again. All right, so you can see it ran. And that should be, it's going to be Wizard Sauron, so it is going to be DUAL1, is that it? And so you can see it made it. You'll also notice I didn't get that weird foreign key problem. You can't commit here. So you can't commit when you insert the person, because if you then fail, you'll have a person, but you will not have a faculty or a student to match it. So it's got to be a transaction. You can't commit in the end. But you can see that at that point, I made it. So then I'll just go take the family photo. Students, just the student's interesting. So that's basically the photo of the code. And then that's just retrieving a person and retrieving a student. All right. So all right, there will be a recitation tomorrow. Let's go. I will do 3-3 real quick. I can't even remember which one that was anymore. 3-3. 3-3 is a nightmare to compute. This is the answer that you'd like ideally. It's just basically one line that summarizes a person, a player's performance. So the thing I'm looking for here is that when you do transactions, OLTP, your queries tend to be relatively simple. So if I go up to an ATM, I basically ask for account balances by ID, or I transfer money from one account to another by ID and amount. I'm not asking you to compute the average deposit for all people in Singapore from June to September. So I'm not running decision support. It's simple, and there's updates. So because of that, I tend to normalize the data for integrity. To do decision support, every time, the primary technique for normalization is to decompose a table into two, which means if I want to recover the data, I have to join. And so I'm doing large amounts of data I don't want to join. So that causes you to be big wide tables. So I wanted to give you a scenario where you had to build a big wide table. And so this line is a one-line summary of a player's performance. So it's got batting, pitching, and fielding. I decided not to worry about salary and appearances. So what's happening is you have to do a batting and group by player ID to get their overall performance. You have to do pitching and group by to get their overall performance. Now, if you do group by on fielding, so if you go back into the Llama scheme, the Llama 2017 schema, so we'll just basically go find that schema. Set as default. And you do select, player ID. Sum of home runs as HR from batting group by player ID. Right? That does the obvious thing. Just basically we'll group it. So Hank Aaron had 735 home runs. So that groups it. If you try and do this on fielding, for like attempts, you'd be tempted to think that it does the same thing. But in fact, it doesn't. So if you basically go in here and say, I just want to know, I'm just going to basically go count a star. And do that. Right, you can see that some weird stuff starts happening. So player count a star. So basically, the reason for that is that if you go take a look at this table, okay, star from fielding, I don't group by player ID. You can see that in a single season, it's got the position thing. So anybody ever played more than one position can see that this guy here, Hank Aaron, played two positions, outfield and second base. So if I do a group by player ID, I'm going to get two rows here, not one. So for batting, I get one row, and for player, I get two rows. So what I wanted to do is flatten these things out so that I had a set of columns for each of the positions. The queries that do that, it's just like it's a nightmare. So basically, part of it's easy, which is you do the select and group for pitching, select and group for batting, and then you can outer join those. And then now you've got batting and pitching. You can then do the group by fielding, but then I had to go and select the infield ones, join those, and now I have all in infields. And so I had to keep folding in these columns. And so this thing got nightmarish. And you can see this is a hideous script. So for this assignment, all I asked to do was this part of the graph. So you need to basically do the select and group by for batting, the select and group by for pitching, the full outer join, and then producing the table. So this is the group by for batting. So create a table, batting summary final as, and I'm going to get the sum of the games, the sum of the at-bats, the sum of the runs, the sum of the hits, the sum of the doubles, the sum of the triples, the sum of the home runs, the sum of the RBIs, and the sum of the walks, sum of intentional walks, from batting where the years after 2010, I'm only going to look at seasons where the player had more than 100 at bats, because some seasons are not representative because the person didn't bat enough. So why would I start including that statistically? And I'm not going to look at players who have not had enough at bats in their career for there to be statistical. So these are two common things you do when you analyze data, which is you're going to group and aggregate, but sometimes in the aggregate there are data points that are anomalies, so I'm going to ignore those. And I'm also going to ignore ones that are not statistically significant. This is the one that does the same thing for pitching. So it's the first two from the hideous script. So that is this and this producing those two things. And then all you need to do is to just basically, this is the outer join. So that creates the temporary table, that creates the full one. So all I do is I say, all right, do a left join of the batting with the pitching, and then do a right join of the batting with the pitching, and then take the union. And so that does the outer join. And so it's just those three statements. What I wanted you to learn from this one is the basic concept that there are really wide flat tables that are massively denormalized. This is an example. And then this in a microcosm, I talked about extract, transform, load flows. This is a contrived extract, transform, load flow. It's a bunch of SQL that does it. So you just need to focus on that one. And so if you go back in this hideous script, you'll find the queries that you need. So I'm going to wrap up, and we will go over other questions. So the other question is, will there be a recitation tomorrow? The answer to that is that yes, there will be recitations on Saturday and Sunday, and also I'm available probably for appointments some of those times. I just don't know when they're going to be yet. But I do need to wrap up now. So I will go back when I'm done here later on tonight. I'll answer any questions that are on Piazza. And I will also post, I think the recitation tomorrow is going to be in the morning, but I'm not positive. It may actually be relatively early in the morning, so you might want to check Piazza, but there'll be recitations tomorrow and also on Sunday. So I'm going to wrap up now, and I'll go answer the Piazza questions later. All right. Thanks a lot, everyone. Ferguson out.